Hello, everyone, and welcome to another topic in chemistry. This is our last topic as we continue to explore and understand more about stoichiometry and the applications of that mole ratio. So go ahead and set up your get started setting up your focus notes today. The date is February 19th. Actually, this is more of my introduction slide. I'll have another slide where you set up your notes. But anyway, the essential question for today is, what is the relationship between a change of something called enthalpy to heat of reaction in a chemical change? So it's an extra part of a balanced equation. Instead of just the chemicals, what's happening with energy? So for our bell ringer today, though, I want to do a review of our last topic on percent yield. So let's imagine you had this information. You perform an experiment in which you form 2.76 grams of copper. According to your hypothesis, you should have produced 2.43 grams of copper. What is your percent yield? And explain why it is not 100%. So spoiler alert, I know it's not going to be 100% because I know these two numbers are not the same. All right, let's do this problem together. So here's all that same information. So let's review. Percent yield is saying, how close did I get to 100%? Meaning, how close did I get in my lab to the answer I predicted I would get? So the idea is what was my actual number divided by my theoretical number times 100 equals percent yield. Okay, so actual means something you really did, something you did in the lab. You perform an experiment. 2.76 grams of copper would be the actual. The hypothesis said it should have been 2.43. So hypothesis is your clue that is your theoretical. So 2.76 grams of copper is what I actually did in the experiment. 2.43 grams of copper is my hypothesis, my predicted, my theoretical. I times it by 100 to get it into percent because grams of copper cancels. 2.76 divided by 2.43. I get an answer on so grams of copper cancels. I get an answer on my calculator. I look back at my measured numbers. 1, 2, 3, 1, 2, 3. I can keep 1, 2, 3 sig figs. I look at this number for rounding. It does round up to 100 and that should be 114%. Oh, Miss K, how embarrassing. So it would round up. Let me make sure. Yeah, sorry about that. So this should be 114% yield. All right, so 114% yield should be my answer. Why is it not 100? Okay, let's think about this. I said that I measured 2.76 grams of copper, but it's not possible to get more than 2.43 grams of copper. So that tells us that in lab, when I measured grams of copper, it wasn't just copper. There must have been something else in it. Maybe when I was filtering, one of my other chemicals got stuck on the filter, or maybe it's still wet. The solution, the water didn't all evaporate yet. So some of those molecules are still in there. But something is mixed in with the copper. I'd have to look through my procedure to figure out where my mistake was, but the copper would not be pure. That would be explaining why my percent yield is higher than 100, and then would help me explain my error. All right, so that is a review of percent yield, our last topic. Okay, now let's get into our new topic. Okay, so now set up your focused notes. So for today, to guide your notes, if it's in red, you write it down. So heat of reaction, write that down. Write in whatever date you're taking these notes. Heat of reaction is our focus. And our essential question is, what is the relationship between a change of enthalpy to the heat of reaction in a chemical change? So again, the idea is that instead of just talking about the chemicals in a chemical change, we're also going to be talking about energy. All right, pause the video if you need more time setting up your notes. Otherwise, let's get into it. So you remember that we've been talking about stoichiometry this unit, and stoich is all about the balanced equation and the mole ratio, which I refer to as the switchover step because that's how you get from one chemical to a different chemical using that practical application of the balanced equation to figure out something in a chemical change. But we've been ignoring something. Sure, we've talked about reactants and products and moles and all those good things, but we need to talk about energy or heat. A thermochemical reaction either gives off heat or takes in heat. So instead of just thinking of a chemical reaction, which is just the chemicals, thermochemical thinks about the chemicals and what's happening with heat. That's the new thing we need to talk about this last unit. We measure that heat in kilojoules. The abbreviation is kJ. So when you see a given piece of information that the label is kJ, that's your hint that we're dealing with energy, specifically heat energy in these equations, but that is what that number means. And then that would guide what your practice would show. Now, just to give you some context of what a kilojoule is, it takes 4 kilojoules to raise the temperature of 1,000 milliliters of water 1 degree. So if you had 1,000, like a liter of water sitting in a pan on a stove, and it was sitting at room temperature to like around 22 degrees Celsius, if you wanted it to get to 23 degrees Celsius, it would take 4 kilojoules of heat added to the water to change that temperature. So that gives you sort of a just sort of a reference of what a kilojoule might be in terms of heat. There's 2 versions of thermochemical reactions, or the way we think about heat. One of them is exothermic. Okay, so therm is how we know it's dealing with heat. Exo, like the word exoskeleton. Do you remember from your bio days? Where's an exoskeleton? It's on the outside, right? So an exothermic reaction gives off. Heat is going outside. Heat exit. So X is kind of like exit. So thermal is the heat part. Exo means that heat is leaving. So what that means is that if you were standing near an exothermic reaction, you would feel that heat as it leaves. So the surroundings feel hot in an exothermic reaction. So this would be a generic representation. You have 2 chemicals that make a new chemical. When they make that new chemical, because this new chemical is lower energy, it can release some other energy to make it, because now it doesn't need as much. Remember, that's one of the whole reasons that chemical reactions happen, is chemicals are trying to be more stable. So that's what this is showing. All right. The other option is an endothermic. If I go back to that same example, an endoskeleton, that's what we have. Our bodies have an endoskeleton, because the skeleton is inside. So an endothermic reaction is when heat goes inside. So it takes in heat. Heat comes in, like indo, like in, right? To help you kind of remember. So then in this case, the surroundings would feel cold because the heat went into the chemicals. This might be useful if you're trying to melt something. Then heat would need to take into the particles so the particles could start to move more. That would be an example. And then there's other chemical reactions like that. So decomposition a lot of times needs to take in energy to break apart the bonds. That's what this is showing. QRK chemical plus added kilojoules produces K plus QR. So to break the bond between these 3 chemicals, I needed to add heat, and then I have new chemicals at the end. So that's the idea behind a thermochemical reaction, and then 2 vocab words, exo and endothermic. So enthalpy is the word we use to describe the heat content of a system. So you've got this idea of heat is coming in, it's coming out. In general, that's referred to as enthalpy, and the symbol is delta H, the change of your heat in a system. So that is what delta H means. So delta H is the symbol for enthalpy, and the delta refers to as changing. So it's how much is your heat changing in a system before and after. An exothermic reaction, your delta H is negative. You have less heat than you did before, right? Because heat was released. So this was the heat of your reactants, or the energy. This is the energy of your products because heat was released. So the products have less energy. They're more stable. Heat leaves the system. So this would be an example. So that example I gave before, so heat is released, so the delta H value would be negative 218 kilojoules. So if heat or kilojoules is on the product side of a thermochemical equation, the delta H is negative. That's what that's telling us. And then endo is all the opposite. Oh, sorry, I'll do endo next. You probably need a little break. I've given you a lot of information. So take a little break, pause the video, do a level 1 question, something straightforward. Define, list, come back when you're ready. All right, so now I want to do endothermic, all the opposite stuff. So an endothermic reaction, the delta H is positive because heat is coming into the system. So if we look at this example, so I have my starting chemical, this is my kilojoules. That means that heat had to be added into the system, so your delta H is positive. There's more heat than when you started, right? So you add in heat, so the energy at the end is more because you added in heat to make something happen, or you added energy to make something happen. So endothermic, delta H is the symbol, enthalpy is the vocab idea. Delta H is positive for endo because heat comes into the system. Delta H is negative for an exothermic because heat is leaving the system. Okay, So what does that look like for real? Let me give you an example. So when you bake with baking soda, so if you've ever put something in like cookies or cakes or something like that, this is the symbol for baking soda. Here's the reaction that happens. You put it in the oven, right? That's what makes something happen to it. It decomposes into, look, a couple different gases. That's what the baking soda's purpose is. It makes your cookies or your cake fluffy because it fills the batter as it bakes with gases. But that doesn't happen if you just let it sit there. You've got to add quite a bit of energy. So that would be the baking from the oven. So the delta H value for this thermochemical equation would be positive 129. Why? Because this is on the reactant side. So is that endo or exo? Endothermic, because heat is being added and the delta H is positive. Then the new thing we're going to start doing is okay, so what I can do is I can relate these kilojoules to anything else in the balanced equation. 129 kilojoules for every 1 mole of sodium carbonate, 129 kilojoules for every 2 moles of sodium bicarbonate or baking soda, 129 kilojoules for every 1 mole of water. So you can use it as a new conversion. The delta H is a conversion, the number of moles from the balanced equation. So the delta H is equal to the number of moles from the balanced equation. So your delta H, 129, is equal to the mole ratios that we used to get. So that is why this still fits into stoichiometry, because you're still getting ratios or equivalents from the balanced equation. It's just that instead of going from moles to moles, you could go from kilojoules to moles or moles to kilojoules. So delta H is a new conversion, and it's equal to the number of moles from the balanced equation. All right. So again, from above, so your example would be there's 2 moles of sodium bicarbonate for every 129 kilojoules. So that would be a ratio you could set up in a DA problem. Now, another practical application, instead of just converting from like grams of this chemical to how many grams of water was produced, you could say, if I need to decompose this, how much, like 10 grams of this that I put in my cake batter, how much heat do I need? So that's the idea why this might start to be useful. All right, let's see what this looks like. So a thermochemical equation for the synthesis, so I'm making carbon dioxide. Let's do this example together. Carbon plus oxygen produces carbon dioxide. This is a more stable compound than the 2 elements by themselves, so it releases energy, 393.5 kilojoules. All right, so the delta H would be some version of this, either positive or negative, but this is the number. So then now ask yourself, is this positive or negative? Well, it's on the product side, so it's leaving. So it's negative 393.5 kilojoules. So then is that exo or an endothermic reaction? Think about it. It's exothermic because heat is leaving and the delta H is negative. All of those mean the same thing. Heat as a product, negative delta H, exothermic. All of those mean the same idea. Okay. All right. Do a level 2 question. So find something, explain something, sketch a picture of a thermochemical reaction with heat in it. That'd be kind of fun. So do a level 2 question, take another little break, look back at any parts of the video. If I'm going too fast, that's the beauty of it, video lecture. But take a break and process what you've written down so far. Do a level 2 question, come back when you're ready. Okay, now let's actually do this problem. How much heat is produced if I combine 35.4 grams of carbon with oxygen? So this starts to show you the kind of problem we can do. So if I have, this is what happens with charcoal, like if you're using a charcoal grill. So how much heat is if I have 35.4 grams of charcoal carbon, the oxygen's just freely available in the air, how much heat will I produce with that much carbon? So let's do that together. Start with your given and convert it to moles. So my given is 35.4 grams of carbon, all right? So I need to get it to moles. Okay, so that means I need the molar mass of carbon. I look on the periodic table. I need grams to cancel, so that means grams is going to go on the bottom. So this is still DA. It's still conversion stuff. That's the good news. All of that, I hope, feels familiar, or I'm going to show you another example just to help you catch on. Grams of carbon needs to cancel, so I look at the periodic table. The molar mass of carbon is 12.01 grams per mole. 12.01 grams goes on the bottom, 1 mole goes on top. Grams cancels, I'm at moles of carbon. All right, so there was my first step. I convert to moles. Now you can do the switch over step, but you're going to switch over to heat instead of switching over to another chemical. So look at your balanced equation. There's 1 mole of carbon and there's 393.5 kilojoules. So set up your bracket. I need moles of carbon to cancel. Look at the balanced equation. There is 1 mole of carbon. And then I'm switching over to heat from the balanced equation, 393.5 kilojoules. Moles of carbon goes away. I'm at kilojoules. That is what the problem is asking for because that's asking for heat. So I'm ready for my equal sign. Multiply all the numbers on the top, divide all the numbers on the bottom. Calculator gives us this answer. All right, let's check our work. Make sure I get my sig figs right and rounding, like the mistake I made in the bell ringer. Oops. All right, 1, 2, 3 sig figs. 1, 2, 3, 4 sig figs. 1, 2, 3, 4 sig figs. I can keep 3 based on this number. So I can keep 1, 2, 3 sig figs. I look at this number for rounding, which it does round up, but then I'm going to need a placeholder. So a 1,160 kilojoules produced. That's important. Why did I need to say it was produced? Because remember, this was an exothermic reaction. If I didn't have that word produced and I just said 1160 kilojoules, we wouldn't know, wait, was that endothermic or exothermic? So putting the word produced is important. That's part of the label and you can't leave it off. If you leave it off, we're going to assume it's endothermic because I'm adding in this kilojoules. That's what's needed, right? You need to put the word produced to show I don't need this much kilojoules. That's how much kilojoules is given off. So again, I'm hoping you can see, oh, okay, yeah, this looks like DA. It looks like all the stuff we've been doing. Oh, it's just that now instead of a mole to mole ratio, it's a mole to kilojoule ratio, still from the balanced equation. All right, one more little piece. I've used this term a couple times, thermochemical equation. It's a balanced equation, but it doesn't just have chemicals, it also has that enthalpy value. If the enthalpy value was given is negative, put the number of kilojoules on the product side. If the given enthalpy value was positive, put those kilojoules on the reactant side. Other than that, it's a regular balanced equation. So let's practice this. Let's do the complete combustion of glucose. All right, well, glucose is C6H12O6. It's a solid, so this is a type of sugar. This is what we're going to, you might recognize this equation as photosynthesis. It's really the combustion of glucose, though in bio, they just call it photosynthesis. Combustion means oxygen is present and CO2 and H2O are produced. Okay, so complete combustion of glucose. Here's my starting chemical. Here's my other reactant. Those are the two things that are present. I know what my two products are. So I've got all the pieces. And then the other thing I need to know, you would look this up. The delta H of combusting glucose is exothermic because energy is released. That's how photosynthesis works, right? The energy is released and then the plant can use that energy to grow and live and be healthy. So the delta H of the reaction for the combustion of glucose is negative 2808 kilojoules per mole. So I put this number in my full equation. Oh, great. Go ahead and pause the video and see if you can write this equation before I give it to you. You know your reactants, you know your products, you know your delta H value, and you know it is negative, meaning it's exothermic. Put it all together. Pause the video. All right, let's see if you got it. Oh, we already have it. One more hint. Negative value means it goes on the product side, but you already knew that. Okay, let's try it out. Thermochemical equation for the combustion of glucose is, do you got it? Here's glucose. You need 6 moles of oxygen to produce 6 moles of carbon dioxide and 6 moles of water, and it produces 2808 kilojoules. So the balanced equation is still important. We had to get a 6 on this side because glucose has 6 carbons in it, 12 H's, so 6 times 2 H's, 6 oxygens, plus I have then oxygens over here too. So 6 times 2 is 12, plus 6 is 18. 6 times 2 is 12, plus 6 is 18. Balanced equation with kilojoules makes it a thermochemical equation. So you would do the balancing chemical part like normal, and then you'd have to be given or look up the delta H, and then you either put it on the product side if the delta H is negative, or you put it on the reactant side if it was an endothermic positive kilojoules. Thermochemical equations. All right. Endothermic or exothermic, we've kind of talked about this already, but what would it be? It'd be exo because heat is being produced. Heat is on the react or product side. It's a negative delta H value, all of that good stuff. Thermochemical equations, kilojoule ratios with chemical mole ratios. That's the new part of today. All right, why don't we do one more of these? How much heat is produced if I had 64 grams of glucose that completely burns? All right, so let's do one more of these types of problems. Start with your given and get it to moles. 64.0 grams, set up your conversion. I need grams to cancel, get to moles. Oh man, I need the molar mass of that big whole chemical. The molar mass of glucose, look up the individual molar masses times carbon by 6, times hydrogen by 12, times oxygen by 6. So carbon is 12.01, but there's 6 of them. Hydrogen is 1.01, but there's 12 of them. Oxygen is 16.00, but there's 6 of them. Multiply, add it all together, 180.18 grams per mole for glucose. All right, go back to your conversion. I need grams to cancel. 180.18 grams goes on the bottom. 1 mole of glucose goes on the top. Glucose cancels. I'm at moles of glucose. So I look back at my balanced equation. Here's glucose. I can relate it to any other part of the balanced equation, but the problem is asking for heat. So now I switch over to heat using that balanced equation. So set up your bracket. Moles of glucose. Look at your equation. There's just 1 mole of glucose in the balanced equation. And then there's this much heat in the balanced equation. So I'm using a mole ratio of moles of glucose to kilojoules from the thermochemical equation. Moles of glucose cancels. I'm at kilojoules. That is a unit of measurement for heat. So I'm ready for my equal sign. Multiply all the numbers on the top. Divide the numbers on the bottom. Calculator says this is the answer. Let's look at our sig figs. This measured number has 4, this measured number has 5, but this measured number only has 3. So I can keep 1, 2, 3 sig figs. I look at this number for rounding, which it does not. So those chop off 997 kilojoules, and we need that label produced. Why? Because this is an exothermic reaction. Without the word produced, it would look like I need 997 kilojoules, but I don't need it. That is how much is produced if I start with 64 grams of sugar, specifically glucose. All right. Do a level 3 question. Predict a situation where we would want to know predicting how much heat is produced. That could be super useful. Think of an example of one. Write that as your level 3 question. All right, welcome back. Let me give you a little summary. You can either use this as your summary or use this to help you write your own summary, but let me just kind of wrap up what we talked about. Chemical reactions also involve energy. It can be an endothermic or an exothermic reaction, heat going in to make the reaction happen, heat releasing because the products are more stable. Thermochemical equation is when you write a balanced chemical equation like we already know how to do, but you add in the delta H value. You can use the delta H of a reaction to figure out how much energy is either needed to start the reaction or produced after the reaction. It's still stoichiometry. You still have a switchover step, but it's a heat to mole ratio instead of a mole to mole ratio. You could still do a mole to mole ratio if the problem was asking for that, but you can also do that heat to mole ratio. That is our summary for our new information today. That brings us to the end of this day of Unit 5. Go back and finish any COSTA questions. Write your summary, either the one that I just gave you or use that to write your own summary. And then I do have heat of reaction example or practice problems posted in today's Schoology folder. It's not anything to turn in, but it's the only way for you to practice this new information and see if it makes sense. Check your answers. They're worked out so you can see the work if you get something wrong, but do that, at least a few of them, to practice today's new information. There are some unit practice problems that you can do related to today's notes. A few of them, that would also be a way to check your work and see if what you learned today made sense. Those are the things that go with today's notes. The other task is that you need to do your Unit 5 quiz. There is a review with answers posted in, depending on which hour you have me. It's either in your February 17th folder or your February 18th folder. Go back and do that review and then take the Unit 5 quiz before our next Zoom, our next class together. So that is your new assignment for today. These things are just all part of your notes. All right. Thank you so much for your attention and your focus as we learned one more application of stoichiometry. We'll see you next time.